that nothing is infallible.
Indeed. So, yeah, we'll start the show.
Okay.
So, welcome back, folks. Happy Garbage Day. Happy Tuesday.
Happy Election Day.
Happy Election Day, yes. We're just going to keep smiling. Are there stress cookies in the back? Is that what those are? So, thank you again. We have some stress bakers in the class. Cookie. So, I have a proposal for you based on sweets. I have an avalanche of Halloween candy left over. My husband overbought and we didn't have as many people. If I bring it on Thursday, will that get more of you in person as a reward? To like
not sure
literally
about more,
sweeten the
but-
pot, I will bribe you with food and candy. Get candy, you know, and we have the good stuff left too. It's not just like, you know, Whoppers and stuff like that. It's like well, Kit Kats are mostly spoken for my son, but I'll try to like get a few. Yeah, he's very particular about Kit Kats, but we got Snickers, we got the Reese's peanut butter cups, licorice. There's nothing that involves mint and chocolate though, because that is just wrong.
I agree.
Thank you. No, there is a bimodal distribution when it comes to mint and chocolate. There are people who love it and people who hate it. And I feel like Erica's the first person that I've learned about in the history of the world to be somewhere like, yeah, take it or leave it. So no mint and chocolate together, I promise that much. Well, mint just like ruins everything around it. It does. It does. I'll tell the same story I told an hour ago. So my mom uses paper plates for dessert at her house, even though she has plenty of plates, because she's always trying to conserve dishes. And one time she had like chocolate cake. It was someone's birthday, served on paper plates, and we're eating it. It's like, this tastes like mint. And it turned out she had stored a bag of mints on top of the paper plates, and they like infected it. It's like, what? You just ruined this cake.
That's terrible.
Exactly. And if you're not like expecting it, it's very jarring. So no mint to contaminate the situations. My husband knows better than that to buy any mint chocolate candy and leave it in our house. But we'll have the other kinds. So I have our syllabus up because I'm trying to remind ourselves what's going on here. So nothing was due yesterday. Get a little bit of a breather. Homework 4 is out right now. That is due next week. Any questions on that so far?
I have a question.
Sure, go for it.
I couldn't figure out what the partial art is supposed to be. Like, I got all my computations, but when it said what does this, I was like, I don't know actually.
So how to get it or what it means or both?
What it means.
Okay,
Yeah, I got it, but I was like, I don't know what it does.
that is a great question. So let me go to where we can talk about that. So question was, what does partial R mean? It is essentially the correlation between the unique part of the predictor and the unique part of the outcome, like what they have in common. So controlling for all the other stuff with respect to both X and Y.
Okay.
So the test of that slope tells you whether or not that variable contributes prediction uniquely. And that partial R is supposed to be a measure of effect size as to the extent at which it does. But it's controlling for both all the other variables in the model with respect to both the outcome and that predictor. That's what the partial part is. Does that help?
Yes.
Okay, because like the squared version, this is slide 22. We're talking about partial R here. The squared version says how much variance it accounted for that the other predictors didn't already. And so then the square root version of that is like putting that into a correlation metric instead of a shared variance metric. So partial R is controlling both X and Y for what the other predictors brought to the problem. Semi-partial, or part as it is known in other textbooks, is not controlling Y but controlling X. So like the semi-partial correlation would just say how related is this X uniquely to all of Y. Not the Y that the other predictors didn't get already, but just all of Y. Yeah, and so that one I feel like is a little bit less useful than the squared version, because the squared version is how much of the R squared did that predictor get? And I feel like that's a directly answerable question. So in practice, I would do semi-partial eta squares for how much of the variance did that predictor or set of predictors working together capture. And then for each individual predictor, a partial R puts that into a correlation metric, or what I call partial Cohen's d, because it's the same idea, but it's in a different metric, standardized mean difference.
Okay,
Okay, does that help?
yes.
Okay,
Thank you.
yes. So both of these would be like per slope effect sizes, but if you want to talk about variance explained, like how much of the R square is due to this predictor, that's where it gets a little tricky, because you can't just add some of them up if they're related to each other. So that's where the extra layers of code come into example 4A and 4B. Okay, other questions?
Page 29.
Page 29. This one, yes. Eta squared for a set of slopes. You have a question, or you just want to hear about it?
I want to hear about it, and they how conducted from step 1 to step 5.
Okay, so the logic is, if you need to test a set of slopes at the same time to get a significance test and an effect size, that's the situation we're talking about. Now, when would you want to do that? So motivation, go back to the equation here, for example, that we're working with as an example motivation. So in this problem, these two slopes, so this is example 4A we've been talking about, differentiate the three groups of self-reported working class. So if my research question is, how much does working class account for differences in education? I can't answer that question with either this one or this one, because these are only two of the three possible differences. There's a third. So I have to lump them together to ask, does this variable as a whole predict income, and what's the significance test for that? And I would do the same thing for these two, because age requires two slopes to delineate its relationship, and then education required these three. So that's the situation we're talking about, is if you need to test a set of slopes together that represent one idea, how would you go about doing that? And the answer in short is, take those slopes out of the model and see what happened. Because then the difference between where you were and where you are now without them tells you how much they contributed. And this is done in terms of sums of squares to make sure that all of the values stay positive. So sums of squares is essentially the numerator of variance. It's like how much information the slopes captured. So to do this then, we would start by getting the model sums of squares. So how much information did the full model capture with everything in it that you want? How much sums of squares was left over from that full model? So those two would sum to the total. So full plus residual is total. We need all three of those numbers in the computations below. Then you fit a model without the set of slopes you care about and see what the change in the sums of squares is. So we compute this new thing, which I'm labeling SS effect, meaning what is the effect of these things we just took out, and what it was before minus what it was now is how we get that. So the change in sums of squares. Then that is the numerator in either of these effect sizes. So on the semi-partial, it's how much of the semi-partial R square is computed as information difference between the models relative to total information, and partial version is information difference from the models relative to that plus residual, so what the other predictors didn't already get. And so then you would do this for each set of slopes to be tested. And you can do this out of one model that has everything at once so that you can see the unique contribution, or you could do this in a layered fashion where you add in things one by one and see what happened. And that is honestly more common in practice, although I don't think it should be. But I built Homework 5 to map that scenario instead. It's known as stepwise or sequential or hierarchical regression when you do it that way. Okay.
So sum of square full, it's the sum of square of 7 slope.
Yes, yes, exactly. Like how much information did the 7 slopes capture, and how much is left over? Those
So-
together are the total.
Sum of square of residual is the E of the 7 slopes model.
It is the E before dividing by degrees of freedom.
E before.
Yes, so let me go to one of the tables here, like in the 7. So the shorter version is here in this data output. So we have, this is the 7 slope model. So we have information captured, then we would normally divide that by number of slopes, and then this is like information per slope captured. Same idea on the bottom, information left over, divided by a number of slopes we could have still added is this term, which is like information per potential slope, which is residual variance as we otherwise know it. And then these two sum together. So the total is this number, and that's what you would get from the empty model, because everything is residual in that model. Nothing has been explained. Does that help?
It's how. And also, I have one more thing about the sum of effect. It's a sum of square of effect.
Yes, so the sums of squares effect is what I'm calling the difference. So what the full model got versus what the model got without those slopes. Then that isolates the contribution of those 2 or 3 slopes you're testing specifically.
Without the slope, you mean empty model?
Not empty, but just without those slopes. So let me show you a more concrete example. I think we did mostly Stata code before. I feel like we haven't been as much through the R stuff. Does that sound right? Do we care?
It's done about equal, I feel.
Equal? Okay, I want it to be equal. I'm not trying to play favorites, even though we all know how I feel about R. But I'm getting better at it. So in Stata, the way that you would get significance tests is a separate command that does not involve fitting a different model. So I like this approach because it doesn't require you to take that extra step. So after you run the model that you are interested in, so like here is, way back here, we've done this one several times, I think, so this is the 7-slope model. Okay, we run that, get the stuff out. I'm storing the results, saving some of them, so I'm getting out the terms that I'm going to need to compute the effect sizes later, SS residual and SS full. Getting effect sizes for the individual slopes, putting the model results back into memory so we can ask for more things. And so then this test statement says, hey, what if this slope were 0 and that slope were 0? I want an F for both of them jointly. So it's built from just each combination, but also their covariance. And so this F test says that if I took these 2 slopes out of the model would be significantly worse. It would hurt the R square. So that means there is a contribution. And then the next logical question is, by how much? Well, it's significant. Right, but by how much? Because significance depends on what? Two things mainly. Sample size, right? So if I have 1 million people, everything is significant, and that word doesn't mean anything at some point. If I have 10 people, nothing's going to be significant. So knowing whether the difference is significant is not the entire story. We need to know by how much, and that's where effect size comes in. Now, unfortunately, there's no straightforward way to get effect sizes out of this. So as a supplement, then, I wrote code to do that. So what is happening is that this code is omitting the 2 working class predictors. So it has only age and education. So that I'm fitting that model. I don't actually care what the model results are, because this is just a way to get the unique contribution of those 2 slopes. So that's why I have the word quietly. It means don't print the output. So then I'm saving SS effect is what the SS full was that I got above. So I stored that one somewhere up here somewhere.
I think you went past.
Yeah, I went past it. There we go. There it is. So I saved that number there. And now I'm saying go use this number to compute the unique sums of squares from this model. And then I computed the 2 effect sizes as given in the formulas. So I did have to go to the extra step of fitting a nested model, as it is called, a model where it's a subset of the one you started with, to get the sums of squares out of that model so that I can compare it and make the effect sizes. So now my answer is, so how much worse is the model without these 2 slopes in it? Significantly worse. Yeah, but by how much? Well, it depends on how you ask. So if I took those 2 slopes out of the model, my R square would go down by 0.043. That's one answer. If I took those 2 slopes out of the model, the R square that would be left over after controlling for the other slopes goes down by 0.056. So I'm not trying to be funny. I'm trying to actually define it. And if you're like, what did you just say? That
was the laugh part.
Yeah,
sorry.
just no. Like that is, I don't see how that's helpful. And so in practice, people will sometimes just say eta square and not tell you which one of these it is. And you can see why that would matter quite a bit. if I continue adding things to my model, so right now I really only have 3 variables. I have working class, age, and education. What else predicts income? Unfortunately, probably more demographic variables like your gender, your race, where you live. Like there's a lot of things that go into that, right? So let's say that I go into my data set, I start adding more things. Well, partial R square is going to go up because I've just explained more of the variance. And so then this is the change in the R square for the R square that would have been there had the other predictors not been in the model. Well, you added more predictors, so now it has like, it looks proportionately bigger.
Yes.
Whereas this one, semi-partial R square, is going to be the same. It's how much of the total variance is this responsible for, regardless of how much of that total has been predicted by other things or not. So semi-partial generalizes across studies better for that reason, because it doesn't matter what else is in the model, this answer should be about the same. And I did the same thing then for age. So testing these 2 slopes for age, they significantly improved the R square. Same thing for education. Now it's 3 slopes being tested at the same time, and then I got the corresponding effect sizes by fitting a model without those terms, seeing how the sums of squares changed, and feeding that into the formulas. To do the same thing in R looks a little bit different. So here's the big 7-slope model. We've been through the output for this a few times. The total R square for the model is 0.29-ish. So I added a function that links the tables in the summary together and adds on the confidence intervals. So that's this. So there's less code than there was in the previous examples. I wrote a function that adds all the effect sizes on. So I computed D, R, and the squared versions of everything to add to these. So in this case, like semi-partial R square, we just decided we like that, right?
Mm-hmm.
It's how much of the variance that thing is responsible for. Well, I can't use this number, even if I can compute it, to talk about the effect of working class. Because if I try to add those together, it's not the same as what we just found. Because they have something in common. They have a common reference group. So like those 2 together are not additive in the same way. So that's why we have to go to the trouble to test them specifically and take them out of the model and see what happens. And the same thing would be true for the others that group together like this. So to do that in R, I did the same process. So, and you laughed at this last time, and I realize why now. So model 2, no class, because it's model 2 without those 2 variables in it. I then fed that into a function that I found online that does the F test part, and then I was able to add to it to do the calculations. So essentially automating the process that I showed you in Stata to a greater extent. So the function I created is called R square change F. Reduced model, it wants to know what is the subset model, nested model, what's the original one, and what is the name you want to call it on your output. And so then the results of the function look like this. It puts it all together. So the first column is the R square for the overall model. The second column is the increase that resulted from those 2 slopes specifically. Those 2 slopes then, here's the hypothesis test for that. So numerator degrees of freedom, denominator F and p-value in scientific notation. And then I stacked on these 2 numbers. So this semi-partial R square of 0.04276 is the same number as the R square change of 0.02 or 4276. That is not a coincidence. That is what this is doing. It's like as if we started with the model without working class and we added it, the change in the R square is that number. If we start with the full model and we take it away, the change is that number. So R squared change is semi-partial correlation squared. They're the same value, but to make that point more explicit, I printed a column with that label because I thought that might be helpful. So then I did the same thing with the age slopes, fit a model without them, and the education slopes, fit a model without them. Okay, questions? I'm going to move my left arm because I got a flu shot this morning, and the nurse said I need to keep moving my arm. And she also said I need to drink water, so I didn't even bring soda today.
Oh,
I know. I may very well be drinking some unhealthy things this evening, so I probably should get the water in while I can.
And afterwards.
Yeah. Hey, all right, how are we doing with this? Is this starting to feel a little better? A little bit? I know there's a lot of moving pieces and a lot of numbers. I was torn between making functions and code that just gave you the things I like versus giving you all the things that you might come across. And I decided on the latter because I don't want you to be like, well, I don't know how to make this, and Reviewer 3 wants this version instead. So just the take-home message is I like semi-partial correlation squared if you want to talk about R-square and variance changes. But you have to lump slopes together to make that correct in predictors that have overlap. The results section then, this is what it would look like if I were making a results section in a manuscript, and I need to italicize that. So let me just walk you through my thoughts on this. First off, good labels. All right, do not put LVU in a table that someone is supposed to know what that means. Okay, you know what that means, but even if you show your data set to a friend or a supervisor, they're not going to know what that means. So real labels, that's number one. Number two, if you want extra credit in tying these to an equation, like I could write beta 0, this is beta 1, this is beta 2, but do not ever just write beta 0, beta 1, beta 2 and expect them to know what that means. You laugh, but no, I see this all the time.
I know, I'm picturing like articles that I've read.
Yes.
Where they do that abbreviation, it's like terrible.
Yeah, like, no, give your reader the breadcrumbs to follow what you're talking about, absolutely. And be consistent, I think, too, in whether you're using title case for things or just capitalizing the first letter. It makes it look nicer. Another thing, I'm calling this column estimate. This is an accepted APA abbreviation for estimate, but you might have to define it in a note if it's not. Likewise, what do you think this column stands for? Standard error, that's another accepted one. Now, what's next to it normally is T. I don't have that in my table. Do you know why? How do I make a T?
Estimate divided by standard error.
Yep, you can make your own T if you want to. T is just a means to get P. Now, the way that I've labeled this is not p-value, it's p less than. Because then I don't have to write the less than signs in here, and I can just say 0.001. And note that there's no leading 0 on these p-values. So at least in APA style, you do not need to provide leading zeros for any number that can't go above 1. So correlations and p-values come to mind for this. This can save a little bit of clutter in your table if you can remove that first digit that will never be needed. Next column over, Cohen's D, because I didn't want my readers to have to pick which effect size they care about. I'm just going to give it to all of them. And I don't have it labeled as partial because no one talks about it that way, even though it has the same partial interpretation of what it brings uniquely after controlling for the other predictors. So D's have leading zeros because D's can go over 1, and R's do not because they cannot. And one last thing, this is a nitpicky thing. Those of you who've had me before and I've graded your writing. Erica, what am I going to say? She's giggling back there. Align the decimal points. So this is right aligned so that everything's on aligned. It makes it a lot easier to read. If you want to put p-value stars in, put them in a separate little column next to it that's hidden so that everything still stays aligned. Don't make the asterisks move your values around. And then one more thing. I'm going to put you on the spot again. What am I going to say about this right here? A real minus sign. So inside the Insert Symbols menu, more symbols. Dig through this until you find mathematical operators like minus sign. And you see here it says you can assign a shortcut key. Like mine is Control M for minus sign. So then you don't have to go and hunt for it. And once you, like I pasted this table in from Excel, and these were dashes. Find and replace, minus sign, dash with minus sign. It's that easy. And the reason I bring this up is because it makes your writing look sloppy if all of your punctuation is a dash. Like learn the right dashes and it will look like you've spent more time preparing results. It creates a better impression. So like I know the difference between dash and minus sign is trivial, but it looks nicer. And copy editors who are publishing your work will be happier with you as well. So in terms of how to compute these effect size, I gave the formulas in a note. That way there's no ambiguity as to which one I mean. So I have those values right here. And then the results section, I presented the full model first, the results for that, and then described the unique effects of each combination. So talked about the contribution of working class and then the mean differences between those as the specific model parameters. Then did the same thing for age and then the same thing for education. So, and I have a note here too. The rest of the text would need to emphasize why it matters based on your research questions, that the predictors had significant effects. So like this is very generic. What is missing from it is the caveats that bring the reader with you. Like, in reference to research question 1, parenthetical, reminding them of what it was, we found a significant effect of this, da-da-da-da, thus, and then you bring it back to like why the reader should care. I can't put that in here because I don't have like a compelling story, but those are the pieces that would need to be added, is the context of the results. Like, why are you telling them this? Why should they care? It should be answering questions. And that's the end.
Okay, question.
Answering questions, indeed.
If you could scroll down this a little bit. In your table and also in the paragraph, I didn't notice a reference that you use education, I believe 11 and 12 years as like the reference. When you created your model,
Yes.
Should that make a difference or no?
Yes, so this is,
And maybe I missed it trying to skim through it quickly.
so because this example is building on example 3, like where I would have described the piecewise coding,
Okay.
like this was like the next
So
layer.
this is still part of the same paper description.
Yes. Yeah, this is the new
Okay,
part
but
that would
if
pertain
it
to that.
was a separate, you would want to include that in this.
Yes, you would absolutely need to describe how your slopes are created and what they mean as a result.
Okay.
But I tried to do that in the interpretation. So for instance, for education, annual income was expected to be non-significantly higher by this much from 2 to 11 years, higher by this much to 12 years, and then higher by this much per year after that.
Right.
So
No,
I'm still
right,
trying
no,
to put it in the
I
context.
understand the stepping. I just
Yeah.
wondering what
Yes.
that one piece I did not see. Thank you.
Yes, because it would have already hopefully been
It would
shown
have
in
already
the
been
transcript.
mentioned.
Yep, exactly.
Perfect. Okay, thank you.
No problem. Other questions? Then I think we made it all the way through 4A. I think we did.
Wow.
I know, right? It's only 10 pages. No, this is nowhere near. I think my personal best is somewhere around 40 for one handout. So, yeah, no, seriously. Don't save. I don't know what I did to save it, but we'll cancel, just in case.
Oh, you changed the symbol.
I say change the symbol?
You changed
Oh,
it from
I made it italic. That's right. Then we shall save. Yes, also notice that if you're using regular letters as like stat things, they get italicized. Like P, D, R, F, those things all get set off. Like I didn't italicize eta squared, I could have, but that looks different enough that it's probably not strictly necessary. So that's another convention.
Is use of equation editor also acceptable?
So I like the equation editor because it aligns things nicely, but you can also find these symbols in just regular text.
Right. No. Right. I was just wondering because I use that one a lot.
Yes.
But,
Yeah.
But I know you can find it this way too.
Yes. Did I teach you guys how to make these things? Did I do this? Do you want to see it again? If not, how to make equations in documents? Do we have interest in that? Why not? So I'm going to open a new one. It's easier than you think. So the insert menu, you can insert equations. Alt equal sign is the thing that does that. Move back to the left-hand side. So y, for instance, now the first thing I need to do is make a subscript. Actually, let's do income instead. Now, subscripts, you would have to go up to like, oh, where's the thing, and where's this, and like dig for it, and it's annoying. The equation editor cancels that. It actually uses a LaTeX convention, if you're familiar with that, So underscore, and then an I, and then I'm going to hit the space bar, and it jumps into like what it's supposed to be. Likewise, equals. First thing I need is beta 0. So Greek letters are recognized by their names with a slash first. It's the one that's above the enter key. So for a lowercase beta like this, I would go like that, and then I hit space, and it jumps into what it's supposed to be. If I want uppercase beta, then I would type it that way with an uppercase, and nope, and then it doesn't work. There, now it works. If you want to have subscripts and superscripts, this is the only way I know of to do it. The regular like font doesn't work. So let's say that I want to refer to sigma squared, for instance. I need sigma first.
Spelled correctly?
Yeah, that helps. Sigma. There.
You have my typing skills.
There. Okay. Now to make the squared term, that's a caret and a 2, spacebar, and then an underscore with an E, spacebar, and then it makes the whole thing. And if it's not italicized like you want, you can just fix it either way. And now these are accessible in terms of the format menu, so you can turn it, purple or blue or whatever you like. Cool. Yeah. Much easier than hunting and pecking for all the weird symbols and stuff. All right, let's see. We did this one already, but do you want to go back over it? Sure. At least re-go over or review. What do we think?
Review, I think is probably okay.
Review is okay. Zoomers, what do you think? Review is good? Is that what I heard? Okay, they say the same thing. All right. Okay, so this is an example that will match your next homework reasonably well. Not a coincidence, right? So this is a hypothetical hierarchical system of models here. So each of the lower ones is nested under the one that we're working our way up to. So this is the strategy that I often see in practice, where they might add in first like control variables or covariates like control for age or socioeconomic status or mother's education or things that people know in the literature should be related, and yours is like supposed to be above and beyond that. So if I start with the first model here, this is an empty model. All it does is say, you know what my best guess for everyone is? The mean, the end, bye. That's it. So it's the worst we can do in terms of prediction. Everybody gets the same exact score, the fixed constant. So in terms of R square, it would be 0. All of the variability would be in the model at that point because it would return the same variance as if you just asked for variance in descriptive statistics for the outcome. So I add predictor A that has 1 slope. It reduces the variance by 10%. If the slope for predictor A is significant, then by definition, that change from 0 to 10% for my R square is significant too. Because it's the only thing that could have made that happen. And this is the effect size for it. Now if I add another single slope and do it again, same idea. The total overall R square, let's say, improves up to 0.3. The F-test for the model would test this 0.3 for 2 slopes. But I also want to know, did the new thing help? Well, in this case, the only new thing is the 1 slope. So if that 1 new slope is significant, the change in the R square it creates must be significant as well. 1-to-1 correspondence. Then we get 2 new slopes. So let's say we have a through-group variable that takes 2 slopes, or you have a linear and quadratic slope for something continuous, something like that. It further improves the model, going from 0.3 to 0.6. And now we have a quandary. The F-test for the model tells us about A, B, C, and D put together. It's not going to tell us about C and D uniquely. And the change in the R square that we see here could be due to C, could be due to D, could be due to either. So this would be a situation in which we need to do the extra steps I just went over to test the 2 slopes jointly by taking them out of the model and seeing how much worse it gets. And you can get an F and an effect size for that. So this is the idea. And then here are the ways you can do that. In SAS, there's a contrast statement. In Stata, you can use test or nestreg is something I'm going to show you in the next example. In R, you can do it with GLHT or a new function I found that fits these hierarchical models directly. So it saves a step. Yes, in Stata there is a way to do all 4 of these at once. I want to show you. It's glorious. I just found it this year. It is. Okay. I have a few more slides about sort of unexpected things. I feel like maybe that would be good instead of more code. We take a break from code for a little bit? Yeah. Or a little bit, we'll see. So there is a term that gets thrown around in these sorts of models called suppression. And it basically means things didn't work out the way you thought they would. And it looks weird, but there are reasons why. So in general, the semi-partial R, or the standardized slope if you want to go that way, the unique contribution of a predictor is going to be smaller in magnitude than the bivariate version. So like how correlated X is with Y just period is going to be larger than how X, like the unique part of X is correlated with Y. Does that make sense? Maybe. Okay, picture time. That does not make sense, I can see. Here, back to this. So if X1 and Y are in the model all by themselves, okay, then X1 gets credit for A and C. But then once X2 comes into the story, the contribution of X1 is reduced to just the A part. So the unique correlation of X1 and Y is going to be smaller in most cases than what it was originally before we controlled for stuff. That's what I mean. So bivariate relations are usually larger than unique relations, is what this is saying. Back to there. But this is not always going to be the case. There are certain combinations where the unique relationship can actually be stronger than what it started out with after controlling for other stuff, and it can change directions. Yeah, it can happen. So this is called suppression when it happens, because the idea is that the relationship between the predictors is suppressing the real relationship between the outcome. So this happens in 3 conditions. If the correlation of your first variable in Y is positive, and the correlation of Y and your second variable is positive, then this can occur under 3 situations. If the correlation of your first variable with Y is less than the correlation of your second variable with Y times the correlation between the two, this one, which is the opposite, or this one. This is the one that I see in most in common, which is why I bolded it. The correlation between your predictors is negative. That screws things up in terms of what you would expect to happen. So here's an example that I borrowed from a regression textbook. Let's say that we are looking at sales success as our outcome, as predicted by assertiveness as our first predictor, and record-keeping diligence as our second predictor. So do you think that people who are assertive are good at keeping records?
Sometimes.
Maybe, sometimes. Well, in this example, they were negative. They're negatively related. So people who are more assertive have higher sales success. People who are better record keepers have higher sales success. But then the 2 predictors are negatively related. So more aggressive people are less diligent at keeping their records in this story. So the standardized slopes that relate, X1 actually has a stronger relationship than the bivariate one, and X2 has a stronger one too. So the negative relationship between them helps each of them do like more uniquely. So this is one of the reasons why you can't just look at bivariate relations and then decide what needs to go in the model and what doesn't, because this kind of stuff can happen. It's still useful to figure out what the bivariate relation is, though. Another thing that can happen is that you can end up with a significant model where it looks like nothing is contributing to it. Or you can have the opposite, which is this one. Each of the predictors is related, but when you put them together, they're not as related. So this one in here, none of these predictors, so this is SPSS output, by the way. I borrowed this from my undergrad instructor. So Y in this column is not significantly correlated with any of the X's. So the first number is correlation, the second number is p-value, the third number is sample size. So if we just look down this column right here, all the p's are greater than 0.05. So it looks on the surface that none of these X's has anything to do with Y. But if you look in the tables, there's several of these have negative relationships with each other. So what ended up happening is that the overall F for this model is significant, and these predictors accounted for 18% of the variance in this outcome, even though none of them on the surface was correlated with this thing. It's unexpected. So their unique effects were actually stronger than the bivariate effects. The opposite can happen. In this example, I have one predictor that is highly related to the outcome, and none of the others are. So then when I put them all in the same model, the F is not significant. So it accounted for 7% of the variance. F is not significant. P is 0.16. The reason for that is because F is not really about the model, it's a per slope estimate. Information captured divided by slopes it took to capture it. That's what F is going for. So I have 8 crappy slopes and 1 good one. So on average, I don't have a good slope. So that would be saying essentially that I only need this variable and the rest are just dead weight. This is why I don't usually do group projects in my classes, right? Because I'm trying to avoid this situation. Because if you have
Dead
one
weights.
overachiever and 8 dead weights, the grade that you get together is not going to be as good as what the overachiever would have gotten themselves. Yes. I'm just keeping it real. I hated group projects in college, and so I don't assign them. But at some point when your classes get large enough, you have no choice, because you can't grade, 37,000 different essays or projects.
You could, it just take a long time.
It could, but then the rest of your job could not get done.
Yes.
Yes, that is the punchline. I'm only supposed to be spending, 16 hours a week on my 2 classes. It's 40% of my job. Not even close. Not even close. What if, can you have a significant model and yet have nothing contribute to it? Yep. Here's an example where I have each of my 5 predictors is highly correlated, not highly, significantly, let's say it that, correlated with each of the outcomes, and then the correlators are, the variables are correlated very highly amongst themselves. So if we think about what each of these regression slopes is supposed to mean, it's supposed to be what it brings to the table uniquely. So each of these has very little to bring to the table uniquely, but together, what they have in common still contributes to R square. So this would be kind of a nightmare scenario, because you're like, I have a significant model. What happened? Nothing in it is significant, but somehow it worked together? Like, that is sort of dissatisfying, but it can happen. All right, so summarizing then. In this unit, the objective was to examine models where we have multiple predictors competing against each other for their share of the pie, for the variance explained, for the part of the house they cleaned. Things that we would want to know then. Do the slopes join together to create a model R squared that's greater than 0? The p-value for F will tell you that, but F is per slope. Keep that in mind. What is the model effect size? R square will tell you that. That's the proportion of variance that's explained. It is also the correlation of the y predicted from your fixed effects with the real one, squared. Is each slope significant? We can check the p-value that goes with the t-test statistic. And then what is each slope's effect size? Partial R or D would be what I'd recommend from that. And then combining fixed slopes from different variables. So like we want to test working class and those 2 slopes, and age and those 2 slopes. We would want to know, like, is each slope still significantly different than 0? We would call that a unique effect. The unique effect is usually smaller, but not necessarily. And so if we have only 1 slope, that's an easy question. If we have more than 1 slopes, we need to request a separate F-test for their contribution and their effect size as well. There, we did that one. Lecture 4 is done. Feels good to finish things, doesn't it? Mm-hmm. Now, because I knew that this was going to be a lot, I'm actually going to stop this recording.